a global constellation of science geeks who, under normal circumstance, would take over a local pub or bar and talk about the latest development in science and astronomy. No prior science background needed, that's the key. It's aimed at the general public, and it gives a chance for everyone to chat and exchange information in an informal setting. So to that end, we invite you to grab a beverage, sit back, and drink in the universe with us. Our first speaker is Linda from the University College London, which is incidentally also where I did my PhD, so love. Linda is currently a postdoctoral research associate at UCL, and she will soon move to Queen Mary University of London, starting a UKRI Future Leaders Fellowship to continue her research in neutrinos. So that's very exciting news, and everybody, massive congratulations from everybody here and the AOT Edinburgh team. And tonight she's here to tell us about the incredible flight of the NITA experiment. Over to you, Linda.
Thank you, Xin. Let me share my screen. Hi, everyone. You should be able to see my screen now. And I don't hear any complaints, so I just assume that's true. Thank you for inviting me to talk about our research in Antarctica. Since I'm the first person going, I'll give a little bit of background, and I'll say a few words about how we get to Antarctica, actually. So first of all, why do we want to go to Antarctica? So we want to go to Antarctica to study some of the most interesting particles in the universe. And for me, these particles are neutrinos. Neutrinos are some of the tiniest particles we can think of. And one thing we know about neutrinos is that they can travel great distances across the universe completely undisturbed. And so if we think of a very simplistic model of the universe, we have a source which is really, really far away from us. And this source can be emitting different types of particles. If the source emits photons, which is the particles of light, and if you think of your traditional astronomy with somebody looking through a telescope, they will be looking at the stars and they will be looking at mostly light. But photons can be stopped by dust or by something as thin as a sheet of paper, for example. If your source is emitting other particles like protons, then protons are charged particles, so they can be deflected. So by the time they get to the Earth, it's difficult to point them back to their origin. Neutrinos, on the other hand, can travel extremely long distances undisturbed. But there's a really big problem with neutrino, which is that they're incredibly hard to detect. Because they interact very rarely, they're also very difficult to see. So one way to get around that is to use a really, really big volume. And so the experiment that I work on, it's called ANITA. And what we do, we use 1 kilometer cube of 1 million kilometer cubes of ice to hunt neutrinos. And let's see how we're going to do that. So the first step is actually to get to Antarctica. So the first step to get to Antarctica is to go to, in our case, was to go to Christchurch, New Zealand, and where there's the International Antarctic Center, and that's where you get all of the extreme weather clothing that you need to get to Antarctica. Then you get on a really cool plane. In my case, we were when I went down in 2016, we were taking down a helicopter, and I didn't know how once transport a helicopter to Antarctica, but apparently that's how it is. You just put it inside the plane, and this picture is a picture of the McMurdo Island that you can see an outline of right here. And then if you look over the ice, you see like a few black dots right here. Here is where the compact snow airport is. So that's where we landed. And if you see right here, there's another black dot if you want. That's where the office was when I was in Antarctica. That's because the experiment that I worked on needed to be far away from, needed to be a safe distance from humans, just in case things go wrong. This is just a picture of the plane we got off from, and then a beautiful people mover to get finally to McMurdo Station. So now that we're there, what are we gonna do? So I work for an experiment which is called ANITA. Anita is a giant radio array. So you can see here a picture of Anita, and all of these white things are radio antennas. What these radio antennas do is detect radio signals. So if you think of your old walkie-talkies from the 90s, well, you know, think of a bunch of those. But then what we do with them is we attach them to a giant helium balloon, and then we let the balloon fly all over Antarctica. So Anita flies at 40 kilometers in altitude. So if you think of when you're on a plane, your plane flies at usually 10 kilometers in altitude. Well, Anita flies at 4 times the height of a plane. So the view of Anita is about 1 million kilometer cubes of ice during the flight. And the idea is that we have a neutrino which is coming from very far away, from maybe outside our galaxy, and it comes in and interacts with the ice. And in the ice, it produces a radio signal. This radio signal is then propagated from the ice, then to the air, and to where Anita is. And that's how we see a signature of a neutrino. Similarly, other signatures that we can see are cosmic rays. So cosmic rays are particles that come pretty much uniformly from all over to the Earth, and Anita can see cosmic rays interacting in the air, and we can see them coming to us directly from below, or even reflected. And they will have a similar signature to the neutrinos, but not exactly the same. So we can actually distinguish the two signatures looking at the polarization. So here's a close-up of the Anita instrument. So you can see this big white antennas, which are the ones that receive the radio signals. Then, of course, while the balloon is flying, it needs power. And that's why we have all of these solar powers right here at the bottom and at the top. One critical part is, of course, to know where the instrument is. So we have our GPS antennas right here at the top. And then an even more critical part is actually our communication antennas. So while Anita is flying, we have very little information about what's happening to Anita. We can, so through these communication antennas, we can have a sort of like connection, which is about like as slow as the first connection of internet connections in the 90s. So you can understand how painful it is to have that little information about your beautiful detector. And then what you can see right here is the brain of Anita. Here is where we have where all our electronics go, and where the processing of the data happens during flight. Here is another picture of Anita, where you can see it compared to people. So it's not a really big experiment. It's actually quite small if you think that it can see 1 million kilometer cubes of ice. And then what I said that we do is that we attach Anita to a giant helium balloon. So here again, you can see Anita on the right. Then for perspective, these are people. And then here is the helium balloon while it was being filled. So the balloon is only 0.02 millimeters thick, and it takes 100 million liters of helium, and it actually takes several hours to fill. And when it's fully inflated, it's so big that you can get like a football stadium inside. Now let's see if this is going to work. So you're hopefully seeing a very speeded up GIF of the Anita taking off. Why did I show this speeded up GIF instead of the video? Well, it's a balloon, so it takes several hours to fill the balloon, but then it actually takes quite a long time to move around, and then once it gets released, it goes up actually very, very slowly. We can watch it again if you want. Here is when it gets released, and it slowly goes up, and then it moves, and then where it starts going. So once Anita takes off, here you can see some close up through a telescope, and you can see how the balloon, the difference between the balloon and the payload. So once Anita takes off, it follows the polar vortex, which blows anti-clockwise pretty much every summer in Antarctica. So here is the flight path that it took in 2016. So we left on December 2nd from McMurdo, and then it followed just the wind blowing anti-clockwise until the flight finished at the end of December in a convenient location, or what was a convenient location for us, which is 125 kilometers from the South Pole. Why is that a convenient location? Well, that's because when the flight finishes, you need to go and pick up actually your data physically. And so 125 kilometers from the South Pole is a place that you can reach. And here you can see a picture from the rescue flight that went to pick up our hard drives. So you can see the parachute and then the Anita detector right there at the end of the flight. One question that I get very often is, how does the flight actually end? So the flight ends because, for various reasons, in our case, is because after 30 days, we were in a convenient location and we weren't anymore taking interesting data. And so it was the right thing to do. At the very top of the payload, there is a small explosive. So when you want to interrupt the flight, there's a really big red button. And what happens is that, no, there's not a physical red button, but what happens is that our PI calls the NASA official, and they have the power to set this explosive going. So what the explosive does, it basically cuts the cord to the balloon, and then Anita falls with the parachute that you've seen. So straight away, about a couple of weeks after at the end of the flight, we went over and picked up our hard drives where our data was saved. And then the year afterwards, in 2017, we went and recovered completely the payload. So how does Anita see the world? So if you think of all of those white antennas, each of those receives a radio signal. So here you can see a visualization of all of these radio signals. And you can see in these red ones, in which you can see a sort of peak. And this peak is what tells you that there was a signal that was received by these radios. And so the analysis works that you can work out at what time this peak arrived at this antenna, what time it arrived to that antenna, what time it arrived to this one, and so on. And by looking at all of those peaks, you can make a map and figure out where your signal came from, so where your neutrino came from, or where your cosmic ray came from. So Xin asked me to talk about one specific Anita analysis, which was we found in our past data sets, actually not this last flight, but in Anita 1 and Anita 3, we found a hint of we found two mystery events, two events that we currently cannot explain. And these are events that look like a shower coming towards Anita. So I showed you earlier that the geometry of Anita events usually are, for neutrinos, are fairly sort of like Earth skimming, we say. Otherwise, they'll be reflected off of the ice. Whereas these two specific events looked like they were coming out of the Earth towards us. There was a very steep angle. If you think maybe like a 35 degrees from the horizontal. So they really looked like they were coming out of the Earth. And we found these two events, and we currently don't have an explanation for them. So, as far as we know, there's no standard model particle that at this energy that could have survived the path through the Earth. And of course, you put this out and then it gets picked up by lots of media. It gets picked up by lots of people with different interpretations. Some people say we shattered the standard model. I don't know. I wouldn't really say that. There were other interpretations that were shown more recently. What we can say is that we've seen two mystery events that we cannot explain. And there's been lots of papers trying to put them and explain them using sterile neutrinos, using dark matter, using maybe a powerful transient source. What does that mean? It means a powerful star or similar astronomical object producing these neutrinos. People have tried to explain it using supersymmetric particles, or it could also be an effect of something more mundane, like uneven ice. The reality is that we don't know yet what these two mystery events are. And there will be a new ANITA analysis coming out actually soon. And I can't tell you anything more than that at the moment, but I just find it extremely interesting that there's so many different interpretations for these two events. And I'm going to leave you with this beautiful picture of these pressure ridges just outside of McMurdo, Antarctica, with some of my ANITA collaborators. So this is the ridges that happen when the the sea ice meets the permanent ice shelf just outside McMurdo. Thank you.
Thank you, Linda. What an amazing show. So I forgot to mention at the start, but if you have any questions at any point this evening, please ask away via the YouTube chat function or via our social media pages, and those questions will be forwarded on to the speakers. So Linda, I'm guessing from your talk, you are conclusively shutting down the parallel universe theory, which is all over the media, which I was unfortunate to help spread, which I'm sorry about.
So the parallel universe theory is nothing but, so the interpretation for these two events, one of the interpretation is that they were dark matter particles or sterile neutrinos. So the interpretation of that then can go even more forward and say where this dark matter coming from, where are these sterile neutrinos coming from. And so one of the interpretation was that these signals would come from heavy sterile neutrinos decay coming from the center of the Earth, and they would be a signature of these like parallel universe that manifested itself at the Big Bang. So according to this theory, at the time of the Big Bang, we hear all the time at the time of the Big Bang, there was an equal amount of matter and antimatter. According to this theory, rather than an equal amount of matter and antimatter, there was matter produced in a parallel universe going backwards. As I said, this is just one of the many interpretations of these events, and of course, the paper itself uses words like speculation. And I think with these two events, what happens most often is that the most simple explanation is probably what is going to be true.
Thank you very much. We do have a couple of questions from our viewers. The first one is, if neutrinos travel in a straight line, when ANITA detects emission from neutrino/ice interaction, do you miss a lot of neutrinos as the angle has to be perfectly right?
Yeah, of course. Yes. Let's see if I can go back to. Yes, because neutrinos travel in a straight line, then our field of view is really just from where ANITA is to pretty much below, to the point of maybe like where the maybe like about 30 degrees, I would say, from the horizontal right here. And one thing that is actually, I don't have a good visualization of it. We miss quite a lot of the neutrinos we miss all of the neutrinos that come from above us. That's simply because we're looking down and our antennas are pointed downwards. And then we miss quite a lot of things that come from below and have to go through a lot of the Earth. And that's because, as I was mentioning earlier, as far as we know, no standard model particle can really survive more than a few thousand kilometers of the Earth at this energy. So the most important part here is to remember that ANITA is sensitive at very, very high energy neutrinos. We call them ultra high energy. Yeah.
Okay. Hi, can people hear me?
Yeah, I can still hear.
Okay, we have a second question from Becky. The question is, how does the effect of neutrino oscillation, as presumably they're coming from very far away, affect the results? So how does neutrino oscillation affect your results? Or is that one of the parameters you're investigating? Is that one of the things you're measuring?
So neutrino oscillations is the phenomenon for which neutrinos come in three flavors, and then neutrinos can change flavor when they propagate. Over these long distances, what we think, if we understand the way neutrino oscillation work, is that neutrinos should completely mix. What this means is that neutrinos come in three flavors, and then even if a source very, very far from us produces neutrinos all in one flavor, by the time they get to us on the Earth, they should be completely mixed. So they should be 1/3 electron neutrinos, 1/3 muon neutrinos, 1/3 tau neutrinos. And because of the type of signature that that Anita sees, we could be able to distinguish neutrino flavors, but we haven't seen enough neutrinos to actually do this type of analysis.
Okay, perfect. And just one last question, which is, do you have a favorite theory to explain the two mysterious events?
A favorite theory?
It's hard. It depends on who your favorite theorist is, I guess, sometimes.
Yeah. So there's quite a lot of theories that involve dark matters. My personal favorite, though, I think is one of the most one of the sterile neutrinos ones, for which the theory is that the sterile neutrino cross section is a sterile neutrino interacts a lot less than your flavored neutrino. So a sterile neutrino is a neutrino that doesn't interact very much. So the theory is that what actually happened is that a sterile neutrino went through the Earth, and then it changed flavor into one of the flavored neutrino, and that's what we thought. That's one of my favorite theory. Of course, there's like quite a lot around there, and it's really difficult to see what really happens. There's a lot more theories also about the different geometries of the ice, and detecting radio waves as well. I don't think we understand radio waves as well as we understand light detection, for example.
Okay, perfect. Well, thank you very much, Linda, for that amazing talk. And thank you very much for all the questions. So now, part of our tradition, we have a little game / challenge this week over the break. And here to introduce it is our resident game master, Rosie. So over to you, Rosie.
Yes, hello. So during the break, we wanted to challenge you to make your own penguins. So we've put together a slide with some origami penguins that you can follow, or you can get creative and make your own, tweet them to us or post them on our Facebook wall, and we will show them at the end. Enjoy the break.
Awesome. Right, great. So now we have 5 minutes for everyone to get creative, top up their drinks, feed their cats, make their penguins, and we will see you back in 5 minutes time. Thank you very much. Okay, welcome back, everybody. Can't wait to see everyone's creations. Please remember to make the penguins and then share your creations with us via our social media, so Facebook and Twitter, as you can see here. Okay, so please get creative and make some awesome penguins. In the meantime, on to our second speaker of the evening, we have Anna, who is a professor of astroparticle physics at the University of Erlangen-Nuremberg and a staff scientist at the German Federal Research Lab, DAISY. She is here to tell us about the amazing Ariana experiment. So over to you, Anna.
Okay, good evening, everyone. Let me make sure I share the right screen with you. So yeah, I for the night, you know, it's late already. I chose the title "Ice Camping to Catch Neutrinos from the Universe," or how one builds a new detector type, because sort of what I'll be talking about is the Ariana experiment. And Ariana is sort of, you know, it's in this stage where physicists get all excited and crazy, where they try new things just because they want to figure out how the next best big thing is going to look like. And so yeah, when I was a postdoc at the University of California, I had the opportunity to go there and to actually experience firsthand what it is like to go ice camping, and yeah, how to actually get creative and build new things. It's not like, you know, as some people may assume that, you know, some wise professor just comes up with, oh, this is how, you know, the next telescope is going to look like. It's a lot of fun and creativity. So let's get started. I mean, yeah, the science case, you know, without having actually known what Linda was going to show, I'm pretty sure, you know, that's how I made my slides, that you heard it from the Anita folks. And you know, not coincidentally, it's actually our slides look all very much the same, because we all of the three talks today have sort of the same science case of why we do this. So we want to find the sources of ultra high energy cosmic rays. So it has been known for many years, like more than 50 or 60 years, that we have these, you know, the red line cosmic rays come to Earth at energies way beyond what we can make ourselves. So, you know, if the people at the Large Hadron Collider, so man's made biggest and largest accelerator, you know, from my perspective, they're like low energy people. They're really not even in the ballpark to what the universe can do. So we know that the universe can accelerate particles to much, much higher energies because they arrive on Earth, but it has been a conundrum for more than 50 years. Nobody knows where they're from. And that is basically to what Linda also already said. If you have a charged cosmic ray, that is easy to accelerate, but it sort of meanders through the interstellar medium, it meanders through magnetic fields, and then when it arrives on Earth, it really, the arrival direction has very little to do with where the original source was. So yeah, you can go over and measure neutrinos instead, or gamma rays, or those gamma photons. They can be attenuated, and also there are different production mechanisms for them. So if you really are interested in these sources of these mysterious ultra high energy cosmic rays, you have to measure neutrinos. So neutrinos it is, and as we already heard, they're really hard to detect. So, you know, we need to come up with how to detect them. And you heard that sort of Anita, what Anita does is, here you have the Antarctic continent. Anita just flies over Antarctica and sort of takes a look at the ice that is down there and watches for a neutrino come up, which is sort of, it has the very nice advantage that it views a lot of ice at the same time, but it has the disadvantage that because you're so far away, you're only sensitive to really high energies. So in many physicists believe that, so when I say really high energies, it means like, let's say 10 to the, I don't know, like 19 or 20 electron volts. So that's just crazy energies. But there are many theorists that believe that those neutrinos that sort of come from the same ultra high energy cosmic ray should be a little lower in energy. So you should go and be a little closer to the neutrino interaction. So the Ariana way was, as it's shown in the sketch here, that instead of flying over Antarctica, you put antennas in the ice. So you put antennas in the ice that then can monitor this whole ice underneath. And then when a neutrino interacts and it makes this particle cascade and radio emission, you see the radio emission actually from within the ice. And sort of there's another nifty thing about Ariana is that, so we had the question before that there's only a very limited field of view around sort of an annulus if you want to use the Anita style approach. But if you build Ariana on what's called Moores Bay on the Ross Ice Shelf, so, those of you familiar with Antarctica, this is Antarctica, this is the Ross Ice Shelf. Just to scale, this is about the scale of France. So we're not talking about something teeny tiny as it looks here, but it's, seriously big. Here's McMurdo Station that was already talked about where you come from. And here on the other side, there's Moores Bay. And Moores Bay has this super flat interface between the ice and the water. So it acts almost like a mirror. So Ariana can see stuff that comes from directly from above because the neutrino interacts, and the radio emission that is made is just reflected back up into the antennas. So instead of just seeing a really small ring around the horizon, we can see the whole sky overhead. So that makes it super attractive, of course, for explosive sources, because you never know where they will sit. So you see here, sort of, this is the nice picture of how it's going to be. And that's what attracted me to do a postdoc in California. And then, they send you to Antarctica, you get all excited. And then essentially everything you do all day is you dig. Because those antennas that look sort of so nicely underneath the surface, well, they must have gotten there somehow, and it usually involves a lot of manual labor. So as you see here, you learn a lot about how to build efficient snow graves. So this is a pit that in the end ended up being almost 4 meters deep. Turns out you can't just build a 4 meters deep straight ditch, because then you're in a ditch, you don't come out, and the snow that you want to dig out, you also can't dig out, because throwing with a shovel 4 meters high is quite complicated. So we did a lot of digging during our field campaign there. And this is mostly what we did. So you test electronics, you build in antennas, you put it in the ice, you see what's going to happen. We've seen this here before, this sort of, it's not like it's the all luxurious science endeavor that you can think of. So yeah, they cram you in an airplane. So we didn't have a helicopter on board because this is a slightly smaller airplane, but you get cozy. You sit on the sides, you just squeeze together, and you hope that you're not sitting right underneath the heater, because that will burn you, but you'll still sit close enough so that you actually are not getting cold. And what you sort of see in the back here, just for interest, this is literally sort of all the electronics and bathrooms and everything you have on the plane. Nothing is shielded. It's just what it is. On the other side, you get to do show-offy things. So this is how our cargo actually gets transported. Somebody has to be super brave and just go underneath the helicopter and just click in a little hook, and then underneath this payload is transported by a helicopter. And in normal circumstances, we don't get to do this, and especially sort of the typical PhD student that tends to sit a lot at their desk, they really don't get to do this. So there's the show-offy pictures you get with it. Then, of course, there's these other nice things. We do a lot of digging, and in the end, I think I've never felt so sore after 3 weeks of digging. So then what you also do when you do this testing campaign, you do a lot of waiting. And I was very glad that one of my colleagues brought a Frisbee along. So I can say now that I really improved my Frisbee skills down in Antarctica, because, you dig up to the station and you could connect to the base and say, yeah, please test whether everything works, and then they'll tell you, okay, let's get back to you in an hour. But that means that within this hour, you have to kind of kill some time, so you do improve your Frisbee skills. On the other side, then, you take a break from time to time. This was a really warm day, so, you could take your jacket off. It was only like minus 10 Celsius or so, and so your temperature feeling really changes around a lot. And you drink sort of one of Antarctica's specialties, and that's Baileys with fresh Antarctica snow. So this is like a Baileys slushy that I think I've never had that good anywhere in my life after, but this is there has to be some perks to it. Of course, the weather is not always nice, and this is sort of the typical question of where do you sleep, because you're all alone on the Ross Ice Shelf. You really are. The helicopter flies you in, and we were a team of 3 people. They unload all your gear, and then they say goodbye, and we'll see you again in 3 weeks from now. And then these things happen. So what you see here is those are the 3 sleeping tents. That's where we all sleep in. You now finally see why you need those red flags, because otherwise you don't even find, the last person has trouble finding his tent. And this is the view to the other side. And what you see here is the science tent, the cooking tent, and the living tent. And this is where we sort of spend our 3-week sciencing. And as you see, sort of tents tend to sink in a little bit in these storms. So this is what it looks then afterwards. So you build the tent really on a flat snow surface, and one storm later, it sort of disappears into that. it is somewhat inconvenient if that happens to you when you're in the middle of the night and you need to come out the next morning, because it means you have to dig yourself out. But yeah, that's what comes with the adventure. And many of my colleagues share this feeling that sometimes you're just in your tent and you're like, this is just such a stupid idea. Who cares about those neutrinos? But yeah, the science we do, it's high-end science. We're developing new technology that you can't buy off the shelf, but in reality, it looks very much mundane. So you have your laptop with gloves because everything is cold. You have the little station electronics here. And yeah, you're doing us on a little bench in a tent. You're trying to put this together and make things work. And then, of course, this is really where you feel like your PhD has been well worth spent. You're on kitchen duty. So what you see here is me cleaning up, actually, because there's snow blowing in all the time. And if you let it sit there, it will briefly melt during the day, and then you get ice, and then people fall. So there's a lot of cleaning the floor going on. And this is where we cook, and this is our supplies. It's mostly dehydrated food that you add water to. Then this was our Thanksgiving dinner. So there's no excuse for holidays. So this is I think deep frozen beef and some deep frozen vegetables. And one should always notice that I think, this is not the picture, but we have one where our Thanksgiving dinner sits on a $25,000 piece of equipment. So, we all have our priorities when it comes to the field. So, and then of course, there's this topic that everybody asks me about. They're like, 3 weeks in the field. The only pictures I've seen so far are from a science tent and a cooking tent and a sleeping tent. So there are these other sort of human needs that one has during that time. And then I say, well, there's also the bathroom tent. And, it's American English, so bathroom tent can literally mean anything that has, what that you may do in a room with tiled floor. But it is essentially just a tent with a bucket. So yeah, that means 3 weeks of no showering. And since, you don't want to go through all those buckets, you have what's here called, you see this nice big letter on it. It's a P. So it's a P bottle, which is just spelled with a P bottle. And you can all guess what's in there. So especially for those, feel free to ask questions about it. I don't want to force it on you, but it has been an interesting experience with being the first woman to join an Ariana team to actually figure out how to use this P bottle correctly and the challenges that come with it. So let's get back to science. So you see here those antennas that we put into the ice. This was more sort of a PR picture with the team and the antennas. We put them in the ice to see whether the detector works. And what you see here is actually a cosmic ray signal. So we heard from Linda before that cosmic rays do similar radio signals as neutrinos. And what we measured really here, this is as a function of time, this really short pulse, nanosecond pulse, being a cosmic ray. And if you're into Fourier transforms, you see amplitude as a function of frequency, you see this very characteristic frequency spectrum. So this is our calibration signal. Our detector works. So we've accomplished in principle that things are going forward. And now you know how physicists are. Let's go build a really big one. So for various reasons, we will start building this in Greenland. So we'll plan for 35 stations, not just prototype stations, but really, a lot of stations going out there being production level. And this is Summit Station in Greenland. And this is, we have not been there, so I can't show you camping pictures from Greenland, but I'm more than happy to once we actually set feet on the ground in Greenland to take a look at what we can do in Greenland for neutrinos. So thank you so much for listening so far.
Wow, thank you very much for that fascinating insight into life on the ice. So last time we had this event, interestingly, I talked about toilets in the deep underground science facilities. And this week we learned about it in Antarctica. Seems like we can never get away from this. Well, I guess it's a very essential facility anywhere. So really interesting. So how long were you out on the ice for, can I ask?
So this is something they also don't tell you. Sort of, when you sign up, they tell you like, okay, 21 days on the ice, and you go, okay. And then everybody internally has sort of this calendar that says, okay, 10 more days to go, 5 more days to go. And then, bad weather hits and Sunday hits, so they don't get you out on Sunday. So in the end, we went, instead of 21 days, we went 27 days. So yeah, it was 27 days without seeing anybody else but my 2 colleagues and being all alone on the ice shelf.
Wow, yeah, of course. It's not just straightforward taking a bus or something to work. When you were there, I guess you're really limited by weather conditions, by getting in and out, huh?
Yeah, so it's funny that you say bus, because the helicopter pilots sometimes complain that they're just used as like bus drivers. But so this is sort of, I mean, this is what they're for. They transport people back and forth. But yeah, indeed. So if you've ever tried boarding a helicopter during high winds, I don't recommend doing that. And since they have to land and we have to pack all our stuff, the weather has to be reasonably clear for them to see something, because also, of course, there's no like radar or any other lighting station. So they have to land on pure view. And that means when they're landing, if you have blowing snow, then they can't judge the depth of where they land. So they cannot have blowing snow. They have to have a clear view, because otherwise they just land too hard and then stuff may break. And this is the last thing you want, that your one ride out has a mechanical problem out on the ice shelf. So
of course.
Better
Couple of questions. One question is the thawing ice in the poles due to global warming effects, or does that affect the experiment? So is the thawing ice in the poles due to global warming affecting the experiment in any way?
So what I typically say is that sort of if we look at this map, where our experiment sits right now, so it sits here, sort of here behind this mountain, on very close to the surface. So for Antarctic ice melting sort of faster, it would have to start melting the Ross ice shelf. And sort of I think we're something like 200 kilometers from the coast. So if the Ross ice shelf were to melt already 200 kilometers from the coast, I basically be quit doing science right now. I'll be building a lifeboat, I think, or something. So we are affected by it, sort of more on a global scale, of course, because research in Antarctica carries a whole lot of different responsibility when it comes to sort of climate change, and environmental effects are a problem. But sort of, yeah, it's we're so deep in the continent that if really things were changing for us already, then we were in way much trouble than we already are. So I think for the next 50 years at least, we'll be fine. But yeah, it is sort of a concern mostly for people who really do research on the outlines of the continent.
Of course. And one last quick question. So is there a particular reason why Iceland was chosen as the next site? That was just
Greenland. Yeah. So this is sort of a.
Oh, did I say Iceland? Sorry, I meant Greenland. Sorry.
No worries. So it is actually this combination of, you need a lot of thick ice and you want it sort of relatively permanently, and you need infrastructure. And so we could build this whole thing at South Pole, but South Pole, as we'll hear in a bit from our IceCube colleagues, is going through a lot of detector upgrade at the moment. So if you, as a relatively new experiment, go like, oh, but we need an airplane too, they'll be like, neutrinos again, go get in line. So that's why, you just for infrastructure logistics reason, you go like, hey, how can we have infrastructure on a different continent? And so the US Arctic program in Greenland, they were very, very accommodating and very much interested in hosting us. So it's essentially, we don't care as long as there's a lot of ice, and we're happy to go to Greenland for now.
Cool. Thank you so much, Anna, for that amazing talk.
Sure.
All right. Hi, everybody. So finally, we're having an AOT first, as far as we know. Our final speaker is coming to us live from the Amundsen Scott South Pole Station by live satellite link. So they are John and Yuya, who are the winter over team on the IceCube experiment. And we also have Jim, who is a professor at the University of Wisconsin and the executive director of the Wisconsin IceCube Particle Astrophysics Center, on call. Jim is on hand just in case we lose the satellite link with the South Pole Station. So without any further ado, over to you guys.
All right. Hi, I'm John.
I'm Yuya.
Hey. Yeah, Jim is about to start sharing our presentation. Perfect. So yeah, with that, let's get going. Since time is tight. The first thing about the South Pole Station, you and I are down here as winter rovers for the IceCube experiment, as Anna mentioned earlier. We got down here in the summer. We got down here in November of last year, and this is just a little bit about getting down here. You actually have to take a couple of specialized planes no helicopters. We're kind of intently jealous of that. To get all the way down here. In the early season, you take a Basler, the smaller plane in the upper left, and then most of the logistics during the later season is done with what's called an LC-130 Hercules. You can see our station manager in his signature outfit standing in front of that LC-130. We do have a passenger terminal down here, lower left, and when we got here, we took a few days, but we were very excited to get out to the geographic South Pole in our big reds. So yeah, that's us just 2 or 3 days after we landed. So yeah, next slide. One thing about the South Pole Station that I wasn't ready for is it's very cold here, but it's also very high. We're actually at 9,300 feet of elevation, which is something, 3 kilometers-ish. And as a result, we're even a little bit higher in terms of pressure altitude, in terms the average pressure of where you'd be in the world. We're about 2/3 of an atmosphere down here, which is surprisingly thin when you first get down here. It takes some getting used to. The elevated station itself is quite big. It's quite spacious, 65,000 square feet. I'm not going to attempt to convert that to square meters on the fly. I'm sorry. But divide by 10, add 10%, something like that. The station itself holds about 42 people in the winter, although it's 150 to 160 in the summer, and it uses 450,000 gallons of fuel, which is somewhere just under 2 million liters, I believe. The upper right hand, you can see fuel being dragged across the continent to the South Pole Station. We use so much fuel that about 2/3 of that comes in on these tractors. It's cheaper to go up, drive across the Ross ice shelf, and then up the glacier all the way to the South Pole than to fly all that weight in. It's called the Traverse, and we get 3 of them a year. It's pretty cool. Lower right is our rooms, a little bit nicer than the tents. You don't actually have to dig them out, but they are pretty small. These are actually the larger of the 2 kinds of rooms you can get here. The smaller gets 3 across rather than 4. And then the lower left is the galley. The galley here is incredible. The food is delicious. It's really nice. In the winter, it's not quite this crowded, so we actually take most of those tables out. But this is how it's set up for the summer. Yeah, and all right. A little bit of the sort of fun we have inside the station. Upper left is some people playing wiffle ball. We actually played dodgeball last night, which was a good time. My arm is still sore. Every week, or every summer rather, at station close, we watch all 3 versions of The Thing. And I learned this year that the first version of The Thing is set at the North Pole, of all places. But the other 2 are set at the South Pole. Then in the lower left, you see a picture that Yuya took of me hanging up one of the window blockers. During the winter, when the lights go out for 6 months, we turn on what's called the Aurora Cam. And there's cameras on top of the station, very sensitive ones that are taking measurements of auroras. And as a result, we can't have any white light spilling outside. So this picture is actually at our outbuilding, and we're covering the windows so we don't get light on the snow and mess with the cameras. And then the lower right is us at station closed dinner. It's a really nice dinner that they put on. We actually have another similar one coming up in a week or so at midwinter. So yeah, next slide. Just a little bit more about the station. Upper left is the station from the side. As you can see, it's quite big. It's actually shaped like a wing intentionally to try and deal with some of those snow accumulation problems that we show up with. The 2 pictures catty corner to each other, upper right and lower left. These have to do with the pole ceremony. Every year at New Year's, the new pole marker is unveiled, and the pole marker that is unveiled is the one that is voted on by the previous winter rovers. It's a pretty fun ceremony. We got to participate in it last year. And then we keep all the old pole markers in a case here at the South Pole. Lower right is our generators. We run 3 of these. They produce something like 600 megawatts apiece. We only need 1 of them to keep the station alive. We only typically run one at a time, but we balance between them as maintenance is needed and things. Yeah, so next slide. Oh yeah, a little bit about the greenhouse. This was the other thing I was doing last night, working in the greenhouse. By Antarctic treaty, you aren't allowed to have soil down here, and you aren't allowed to grow anything you can't eat. But that does mean we're allowed to have a hydroponic system. So in the greenhouse, we grow tomatoes, we grow cucumbers, we actually grow basil, all kinds of lettuce greens. It's a good time. And it's a little more filled in than you see in this picture now. This picture is taken with the grow lights on, which is why it's so yellow. There's supposedly a full spectrum, but so far as I can tell, that means red in the camera. So yeah, next slide, please. This is just a little bit about holidays at the pole. They go all out. This is Christmas. We had a gingerbread house competition in the upper right. You can see that the winning gingerbread house was a model of the station, and then all kinds of desserts. They actually had station volunteers come and bake cookies. I had a really good time baking cookies because I missed baking Christmas cookies. Lower right, you can see half of our Christmas dinner. We actually have to split into shifts because the galley can only hold so many people at a time. It should be about 70 or 80 people in this room. You can tell, obviously, this is pre-COVID times, but this is the summer crew. And dinner, like I said, the galley's great. The dinner was delicious. So yeah, next slide, please. A little bit about the weather. The weather down here is very important. You can't land planes if you can't see the ground. The skiway is just compacted snow, so it doesn't look any different than anything else. So you better be able to see the flags, and you better have an idea of what's going on. So the upper right here, you see Yuya actually marshaling a plane. It's one thing you get to do in the summer. I missed out on it. I'd have to try to do it on the next go around when the sun comes up. Lower left here, you see David, our summer meteorologist. He is actually now at Mount Washington, where they have worse weather than we do here, impressively enough. And then in the lower right, you see David launching a weather balloon. Yep, and then yeah, next slide. There we are. So a little bit about the fun we have here. We've actually learned to go build one of these tents. These are a little bit smaller than I think the ones that were shown previously, but they're meant as survival tents. We learned how to use one of the bags that will keep us alive for 3 days, 2 people alive for 3 days. Although I don't think it works very well in the winter. Thankfully, we never go that far from station during the winter. The next picture, you see the walk to Mordor. Some of the people here, in order to keep fit, decided to walk through the extended edition of all of the Lord of the Rings. Yuya decided the wiser method of participating in that over on the left. Then another fun bit is IceCube is headquartered in Wisconsin. So Wisconsin was actually participating in the Rose Bowl this year, and we were able to send them a cardboard sign wishing them luck. They've been in the Rose Bowl, I believe, twice before, and both times they've had it. Wisconsin has had a team down at the pole, and there's been a similar sign. So we were definitely able to recreate it, which was fun. Lower left here, you see a penguin. You see there behind the penguin is a big orange, which is the signature of the New Zealand Antarctic program. Over on the right here, you see you and me in a big red. But there's also the Carhartt jacket, which is very common for people down here, especially people that work outside a lot and are in and out a lot and need mobility. And so Yuya made a penguin style or a Carhartt style jacket for the penguin as well. Very important. And then the lower right is Yuya and me playing chess out at the edge of IceCube, which was a good time in the summer. It's pretty dark out there now. Picture wouldn't work so well. Just a little bit about the end of summer. We got to go to McMurdo for an LC-130, on an LC-130. Here's a picture of Yuya, for some reason, framing one of the other telescopes down here, known as SPT, rather than IceCube, for the sunset. But it's a good picture of the sunset here. The sunset's only once and rises only once per year. So it was a really nice view. I got a nice time lapse as well. So next slide, please. Yep, more about the sunset. This is our building, the ICL. The telescope is actually under all of the ice you can see in this picture and well outside of this picture as well. So keep that in mind as we're going forward, although I think we're getting tight on time. Yeah, we'll just skip this. There's the moon. It gets bright at night. And then we get to the auroras. The auroras were great. Seeing the auroras for the first time was one of our most exciting things we had here. We were actually out fixing some stuff in the ICL, and we saw it. So a little bit about how astronomy works down here. We're divided into sectors. There's the dark sector where there's no radio waves. Then there's SPT and BICEP, both of which are CMB, Cosmic Microwave Background Telescopes. And then there's also the quiet and clean air sector, which do things that are not astronomy related, and therefore we shall ignore them. It's actually climate and earthquake monitoring, but it's pretty cool. So a little bit about the ICL. The ICL sits at the center of IceCube, which is a cubic kilometer of ice that we have instrumented. And in it, we have one computer for each of our 86 strings. The lower right here is one of these computers. You can see the hardware that runs the strings. There are 8 strings plugged into each one of those cards. Each of the, or 8 detectors, DOMs, plugged into each one of those cards. It runs 60 DOMs total, each of these boxes. But the ICL is also used for staging, which you can see the cargo coming in and out. And this one up here is a picture of you and I went through great effort to get that bench out in front of the ICL after we did some snow shoveling. And we've decided we're not going to do that again. The bench is going to stay on the ICL. So next slide, please. So yeah, a little bit about the science. Like I said, it's a cubic kilometer of ice. Each one of those dots you see on the bottom there is a DOM, a digital optical module. And you can think of them like pixels in a camera. So we're doing a 3D image of the ice. It's, as you can see, it starts about halfway down and we go all the way down to bedrock. Just to give you some idea of how deep we go. The idea there is we want to be as dark as possible. We want the only light showing up to be coming from particles. So if we go to the next slide, we'll talk a bit how we make that light, and I think we can go to questions. So the way this works is we too are looking for astrophysical neutrinos, and we're looking for astrophysical neutrinos for broadly the same reason. They come straight at us, and they don't get attenuated by gas, and they all are also just a different messenger, and we're probing a different force of the standard model. So the way we look at this is the neutrinos actually will turn into a charged particle inside the ice. And when they do, they are going faster than the speed of light in the ice. And this actually produces the equivalent of a sonic boom called an optic boom, or called Cherenkov light, that's essentially an optic boom. And that light is picked up by our DOMs, a small model of which you can see in the lower left here. Half the DOM is a big pixel, empty photomultiplier tube. The other half is some computing that lets it talk to the surface. It's pretty cool how it works. We can save that for questions. And then I believe the next slide will give you some idea of what it looks like, and we'll do questions. So yeah, this is a bit what the detector sees. The size of the pixel here, or the size of the sphere, is the amount of light, and the color will give you the time, the relative time it hit at. Just the top one here is one of my favorites, because what it is there's no light anywhere in the detector except just in the middle, a big boom of light appears. The only particle in the world that can do that is the neutrino. Anything else traveling into our detector to make that much light, we would have seen. So we know for a fact it's neutrino. You can see it by eye. It's pretty cool. It's one of my favorite pictures here. It's big. It's a spin gun, as it were. So yeah, with that, questions. He is here in signature big red, and I am not, because I like to stay cool. So yeah, questions, please.
Wow, thank you very much. That was absolutely awesome. And thank you so much for taking time out to join us here for our outreach event. I think it's really hard to imagine any place these days that you cannot just pick up a phone and call easily. So, but here we really need the good satellite link time. So it's really fortuitous for us that the satellite flies over at a good time for our event, and was very jealous of the Walk to Mordor event. I love that so much. So I was very jealous of everybody on site. And next time I do a Lord of the Rings marathon, I should definitely have to try that. So we have a few questions. The first question is, what's the main objective of the hydroponics? It doesn't seem big enough to grow all the food you need. Is it just for research or entertainment purposes?
So it was originally a research project, and I believe there was originally a full-time staff at the greenhouse, but now it's for what we call freshies. Nothing stays fresh for the 8 months of winter here. We're about to use the last of our eggs, I believe, and those are the things other than possibly cream that last the longest. But if you want fresh greens, if you want fresh tomatoes, you want fresh cucumbers, you got to grow it here. It's mostly for morale purposes.
Okay, perfect. And second question is that how many pole markers have there been, and what is the current one?
There have been quite a few pole markers. I do not know the year the first one started, the tradition of the first one, but I believe the US has been here since something like 57. And I think we have a good 30 or 40 of them downstairs in the cabinets. The current one is a marker design that was designed by last year's Winter Rovers. And it's very nice. It has a star shape that is actually, it's cool. It's raised and there's 12 points in different directions. I don't have a picture of it on hand, but I like it a lot. The previous one was a telescope, which was also pretty fun.
Wow. So do you get to design next year's one?
We do. We actually just completed voting on it. They will not reveal to us what the next one will be until midwinter dinner, which is in about a week. And then we are sworn to secrecy till January 1st. So even if I knew, I couldn't tell you. I'm sorry.
Okay, perfect. And how cold is it outside, actually? Since I'm just looking at you there, he seems like he'd be really warm by this point.
Right now, at least yesterday, it was minus 80 Fahrenheit, something like minus 65 C. It'll get another 10 degrees C colder than that at its coldest.
Okay.
10 or 15.
Okay. I had another question from the viewers, and that's how has your work and travels been affected by the current coronavirus situation?
So we are somewhat fortunate in that most of the lockdowns and quarantines and everything happened after station close. Station is closed for 8 months from about February 14th to mid to late October. And as a result of all the lockdowns happening after that, and the fact that we were free of the virus when we locked out, actually the entire continent of Antarctica is free of the virus, means that we actually did not have to change our procedures down here. Given that there's only 42 of us and there's no one coming in or out. Most of the effect of the virus has been watching things up north, which is, difficult sometimes. But otherwise, it's personally on the station, it does not affect us until October, at which point it will affect us.
Right, because I think you have to fly in and out of New Zealand, right? Who may or may not have their borders open then.
I was going to say, with luck, it will be New Zealand. We've been looking forward to the Christchurch Botanical Garden, but we've been understanding that may not happen.
And I have a last question, which is somebody was wondering, how deep does the sunlight penetrate into the ice depth for the optical array?
The sunlight does not penetrate very deeply at all. That's a very good question. The ice down below is actually very clear because it's been compacted for a very long time. But up top, there's about, I don't know, 30 meters? Yeah, right about 30 meters of what we call firn, which is technically ice, but it looks very much like snow. So it scatters the light. There's a lot of air pockets. The sunlight doesn't get very far in at all. And it's completely dark by the time it's down halfway down to IceCube.
Okay, perfect. Well, thank you so much for, again, for calling in. And thank you so much to all our speakers tonight. That was really interesting and amazing to see so much science going on in Antarctica. So I think our game master, Rosie, has been collecting all the penguin origami that's being tweeted to us. So I'm going to hand over to Rosie to show some of those.
Yes, so I'm just going to show here. Can you see that?
Yep.
Okay,
Yes.
great. Oh. I like the space one. And I think that's what we're going to finish on, but keep tweeting them to us. And yeah.
I love it. It was actually more difficult than I expected to make the penguin. I tried during the 5-minute break, and I'm not sure how successful I was. Right, thank you all. And yes, continue making those penguins and tweet them to us. But in the meantime, that's it, folks. Please follow us on our social media for our next virtual event, which will be in a month's time. And please subscribe to our YouTube channel, and that helps us a lot. So please do that. And we look forward to seeing you at our next event. Yeah, thank you so much for